the group theory lecture number 6. And we've been discussing the symmetric groups, right? We've been discussing the symmetric groups. And we found that, very interestingly, that all finite groups are subgroups of some symmetric groups, okay? So now, today we want to discuss something called partitions. So what are partitions? So let us consider the elements of, say, Sn, which consists of disjoint cycles. Okay, so an example of a disjoint cycle is, for example, if I take, say, 1, 2, 3, and 5 and 6. Okay, and although I'm not saying it, but this means that 4 is just nothing is happening to 4. So that's an example of a disjoint cycle. Another example of a disjoint cycle would be 1, 2, say 3, 4, 5, and suppose there's a 6. Okay, so the idea is that there is no overlap of the elements, that overlap of the objects that these these cycles act on. So these are called disjoint cycles. And an example of cycles which are not disjoints, cycles that are not disjoint, would be cycles like, say, 1, 2, 3, say 3, 6. Okay, so here 3 and 3, they occur in both. And then the other one would be, say, 1, 2, say 1, 5, 3. Okay, so but we are interested in Sn groups and disjoint cycles of this form. Is that clear?
Yes, sir.
Okay, so so let us consider Sn elements, which are products of disjoint cycles, that is non-overlapping cycles, and let's call this, say, pi cycles. So pi cycles, that is, each cycle has length pi. Now for I, say, 1, it could be 1 cycle, it could be a 2 cycle, dot, 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 some positive integer r. And we order these cycles in the following way. We say this is the smallest one, and then PR minus 1, dot, 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 P2, P1, okay? And of course, what they need to satisfy is that all the cycles, when you add them, must give you n, right? So 1 to R, pi must add up to n, right? Okay. Now, these elements, these elements, they form some subset. These elements form a subset of S of n, and we denote that subset. We denote that subset as, say, P1, P2, dot, 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 say, PR. Okay. So, for example, if I take, say, S4, okay, and I say, okay, I'm going to consider the subsets in which P1 is equal to P2 is equals to 2, right? So I denote that subset as 2, 2. So later on, we'll switch to a different notation, but for now, let's just use this notation. So, what would be the elements of this subset, right? Well, we are considering S4, so the elements would be 1, 2, 3, 4, 1, 3, 2, 4, right? And then 1, 4, 2, 3, right? Do you agree? This would be the subset. So there are 3 elements in the subset. Okay. Now, what if I say, okay, I want to instead take, say, 2, 1, 1. Then 2, 1, 1 would consist of, say, 1, 2, say 3, 4, 1, 3, 2, 4, then say 1, 4, 2, 3, and then we will have moved to 2, then it'll be like 2, 3, 1, 4, and there'll be 2, 4, 1, 3, and then we'll move to 3, it'll be 3, 4, 1, 2. Okay, so it'll have 6 elements. Okay, so now what we want to do is that we want to find out what the total number of elements is for a general set like that. Is it clear what we're trying to do?
Yeah. Sir, the 2, 2 in square brackets, that is called S2, right?
No, this is not a group. This is just a set, a subset. So we are considering some Sn group. We are considering some group Sn, and we are looking at elements of this group which are products of disjoint pi cycles, where I goes from 1 to R. And we are ordering them in this way. This is just an ordering. And because we are dealing with an Sn group, all the cycles are n cycles, right? All the elements are n cycles, overlapping or not. So all the PIs must add to n. So we are not looking for subgroups here, we're looking for subsets. We're looking for subsets where we have independent, non-overlapping cycles like this one. These are non-overlapping, disjoint or non-overlapping. And what I'm saying is that if I take, for example, S4, and I look for so all the, in S4, all the cycles in total have length 4. But if I look at, cycles which are non-overlapping cycles made out of 2 cycles, say 1, 2 cycle and 2 cycles, then that set consists of these 3 elements, right? Because S4 has, what is the order of S4? The order of S4 is 4 factorial, right? So it's a huge, huge group. Well, big, large group. But it has only 3, and of course, this is not a group because it doesn't have an identity element, right?
Yes, sir.
So it's a subset. We're looking at the subsets and we're counting the size of the subsets. Okay.
So I could choose 1, 1, 1, 4 ones in the square bracket, right?
Yeah, then you would have a different counting, right?
Okay, got it.
Yeah, you basically just will have 1 in that case. Okay, so similarly, this is another subset.